Morning, everybody. Today we're going to talk about the photoelectric emission or the photoelectric effects. Okay? We're going to look what is going to happen when light shines on a metal surface. Yeah? Now, we will look main conclusions of the photoelectric effect. We will define the work function and the threshold frequency, and we state and use the photoelectric equation. Okay? In the late 19th century, scientists thought wave has a lot of experimental evidence to back it up. But there was a problem. Yeah, you can watch this video later when I send you the slides, but I would recommend you to watch the video that I send you a link of already. Okay? Now, the photoelectric effect was already observed in 1839 by Alexander Edmund Becquerel. What happens if you shine light on to a metal? It can emit electrons. So, how does it work? There is light shining on a negatively charged zinc plate. Now, when the zinc plate releases electrons, the gold foil gets also charged and they're going to separate from each other. Yeah? Okay, so we are looking what is happening when we shine normal light, laser light, UV light onto a negatively charged plate, and what will be the effect, and will be the result the same. And we're going to look at some observations, okay? And how can we explain these observations? All right, the photoelectric effects, yeah. And we're going to look also what is the effect of different colors of light, or actually different frequencies. Okay? Now the setup can be a little bit different, and you could actually connect it to a voltmeter and actually measure the outputs. Okay? All right.
We're in the demo lab with Lonnie, where he set up a photoelectric effect experiment. He has white light impingent on a metal, and the energy of the photoelectrons emitted are shown on the meter at right. If he puts a red filter in the path, now only red photons can strike the metal, and you can see they do not have sufficient energy to eject photoelectrons. If we go to higher energy photons, say go to yellow light, that's shorter wavelength, and higher energy photons, they may be able to eject photoelectrons. And indeed, photoelectrons are emitted, but with a relatively small energy. If we go to higher still photon energy, green wavelengths, that's shorter wavelength still, higher photon energies, we can see photoelectrons emitted at a higher energy. Now we can still go to higher energy photons. Blue photons, photons in the blue region, are the highest energy visible photons, and Lonnie has a blue filter that will pass only blue photons. Putting the blue filter in the path shows photoelectrons emitted at the highest energy. So here's an example of the photoelectric effect. Thanks, Lonnie, for that great demonstration.
Okay. Right. Okay. So what can we conclude from that experiment? That we get a higher output when the frequency of the light is increased. We saw clearly that with red light there was no output, but when we increase the frequency to green or yellow, for first yellow, then green, then blue, we saw that the effect was getting bigger. Okay? Okay. We can also look at the applied photoelectric FET. Just go to FET Colorado and actually you can see what is the effect. If I have time later, I will show you the... No, let's see. We can do it now. Internet is a little bit slow today. Security. Okay. All right. Current, light intensity, and electron energy. Okay. Now, we're going to increase the intensity and we're going to look what is the effects. Okay, let's go to change now here we have red light. And we see that the effect is minimum or not there. Now we increase slowly the frequency and we see with the sodium metal. Now we get a light. And look a little bit at the electrons that are released and their speed. Yeah? So what will happen if I now increase the frequency? We will see that the electrons that leave have a higher energy. Okay? Even more. Okay, now look good at the speed, and I'm going back to the green, this area. Okay, now what will be the effect if I increase the intensity? Will that increase the energy of the electrons? Let's have a look. No, it will not have an effect on the energy of the electrons that are released. Only the electrons that are released increase the amount of electrons that are released are an effect of the intensity. Yeah? So, okay, you can look further and you can also check what will happen if we have zinc. What is the effect of zinc? or different types of metals, okay? Okay, so it is like we need a minimum energy before the metal releases an electron, okay? So, think about this. If you are stuck down in a well and you can't get out, unless you have enough energy to jump out, one. Yeah, this is the same for an electron, okay? So what happens, even the red light will excite electrons in the metal, but they have to overcome that gap. Now, if that gap is too big, the electrons cannot be released, okay? So, what you have to do in order for those electrons to release, you have to increase the energy of the incoming photons, which means increase the frequency, okay? Now, in this case, yeah, high energy, violet, or quantum, has enough energy, and it's like the electron has to overcome this gap. Now, this is very important to know because we're going to explain, we're going to use the work function. Now, the work function is actually the minimum energy or the threshold that the photon needs to excite an electron to get released out of the metal, okay? So the photoelectric effect occurs when light above a certain frequency, and we call that the threshold frequency, is shown on the metals like zinc, yeah? And this causes the electrons to escape from the zinc, yeah? And the escaping electrons, we call them the photoelectrons, okay? So, in the experiment, first, the frequency of the light needed to reach a particular minimum value, as we saw in the applet and as we saw in the video, okay? And if they have reached that minimum frequency, they start to escape from the metal, okay? The maximum kinetic energy of the photoelectrons depends on the frequency of the light. That is very important, and not the intensity of the light. Remember, the intensity of the light only has an effect on how many electrons are released, but not the energy of the photoelectrons. Three main conclusions. First of all, for a given metal, there is a minimum frequency which is called the threshold frequency. Yeah? Below that, there is no emission. Photoelectrons are emitted with a range of kinetic energy. Yeah? From 0 to a certain maximum, which increases as the frequency increases. Yeah? Nothing to do with the intensity. Now, the number of photoelectrons emitted per second is proportional to the intensity of the incident radiation. So the photoelectric current is proportional to the intensity. Okay. Why? First, conclusion 3 can be explained if light is only a wave. Conclusion 2 can only be explained by thinking light as arriving as discrete packets of energy, and we call that the quanta. Evidence of light in C consists of tiny particles, and we call these tiny particles photons, which we actually already discussed a little bit in our previous slide. Okay, the work function. Now, the work function is like you have the electrons that are excited inside the metal, they have to overcome that threshold, that energy, okay? Now that energy that has to be overcome, we call that the work function. So that is the minimum energy to remove an electron from the surface of a metal. The threshold frequency is the minimum frequency of electromagnetic radiation required to eject photoelectrons from the metal surface. Okay. Now, the photoelectric effect of Einstein. It takes a certain energy to eject an electron from a metal surface, and the energy is known as the work functions. Electrons can gain energy by interacting with photons. If a photon has an energy at least as big as the work function, the photon energy can be transferred to the electron, and the electron will have large enough energy to escape the metal. Okay? A photon with less energy will never be able to eject, will never be able to go out. Alright. Alright. Now, work function and energy. The maximum kinetic energy of the emitted electrons is given by, remember that, the energy of the photon minus the work function. Yeah? Okay. So this is the energy of the electron. This is the energy of the photon that goes in the metal. And this is the energy that the electron has to overcome. So, when emission occurs, we use Einstein's equation, so we can actually rearrange the equation. Yeah, HF equals work function plus the maximum kinetic energy. Or in symbols, the energy of the photon equals to the work function plus the maximum kinetic energy of the released electron. Okay, so when the light incident is exactly at the threshold frequency of the photons, just enough energy to free the electron, which is equal to the work function. Okay? So the threshold for frequency times Planck's constant is equal to the work function. Okay? So where F0 is the threshold frequency. So actually the work function equals to the photon energy with a minimum frequency. Okay. Now let's compare a little bit our wave photon model, and let's look at some observations and which conclusion can we make. Now, emission of electrons happens as soon as light shines on metal. For the wave model, we could say very intense light should be needed to have immediate effect. For the photon model, a single photon is enough to release one electron. Observation: even weak low intensity light is effective. Weak light for the wave model, waves should not have an effect. Low intensity means, and we're talking about intensity, fewer photons but not lower energy photons. Observation: increasing the intensity of light increases the rate at which the electrons leave the model. If we look at the wave model, greater intensity means more energy, so more electrons are released. However, when we look at the photon model, greater intensity means more photons per second, so more electrons released. So more electrons released, but we are not talking about the energy of the electron released. Okay? So the intensity has no effect on the effect on the electrons that are released, only the amount. Observation: increasing intensity has no effect on the energy of electrons. Wave model: greater intensity should mean electrons have more energy for the wave model. For the photon model, greater intensity does not mean more energetic photons, so electrons cannot have more energy. Observation: a minimum threshold frequency of light is needed. Lower frequency light should work, electrons will be released more slowly. Now, look at the photon model. A photon in a low frequency light beam has energy that is too small to release an electron. Observation: increasing frequency of light increases maximum kinetic energy of the electrons. It should be the increasing intensity, not frequency, that increases the energy of electrons. For the photon model, higher frequency means more energetic photons, so electrons gain more energy and can move faster. So, important for here to know are some conclusions for the photoelectric effect is that if light is shown on a metal, inside the metals the electrons are excited. They go to a higher energy level, okay? The electrons that are excited need to have a minimum energy to get released, and this minimum energy is related to the minimum frequency, is related to the work function. Okay? Now, the energy of the electrons that are released equals to the energy of the photons minus the work function. Another conclusion is that the intensity of the light that shines on the metal has no effect on the electrons that are released from the metal. It is only when you increase the intensity that it is related to the amount of electrons that are released, so not the energy. Okay, next time we will talk about line spectrum and the origin of line spectrum and electron energies in solids, and a little bit about the nature of light, wave or particles. Okay? I think I discussed already. Now don't forget to watch that video I sent you already this morning. It's very useful and it gives you, I think, a little bit a better idea of the behavior of light as a wave and as a particle, and why we are talking about packages of energy. People who have been doing already, who are doing chemistry, know already part of this quantum physics phenomena. Okay? Have a great weekend and I hope to see you soon.